All right, so today we're going to talk about the trapezoidal rule for estimating the area under the curve. Now that we've done some notation with integrals, we can introduce this rule. It kind of depends, it really involves that integral notation that we talked about yesterday. We're still estimating the area. So this is an estimate. It's important to note that we're still estimating the area. We've not got to where we are actually finding the exact area just yet. We did a little bit of that yesterday with shapes that are recognizable, like semicircles, triangles, trapezoids, and those kinds of things. When your region underneath the curve that you're interested in, when that area happens to be one of those recognizable shapes, that's a little bit different. You can actually go through and do one of the finding the area exactly in that manner. But this is a little bit different. We're looking at trapezoidal rule. This is in section 6.5 actually, not 6.6, sorry. 6.5. The trapezoidal rule. So previously we've used rectangular approximation methods to help us find the area under the curve. Today we're going to use trapezoids to approximate integrals. So the trapezoidal rule to approximate the integral from a to b of f of x dx, use this estimate, which we'll call capital T, and capital T is going to equal, in this instance, capital T will equal, hopefully you all can see that all right, it's not blurry or anything. Capital T will equal h divided by 2, and I'll explain what h is, times y sub 0 plus 2y sub 1 plus 2y sub 2 plus ... so on and so forth until you get down to 2 times y sub n minus 1 plus y sub n. Okay, and I'll explain what that means here in just a moment with that so that you can understand that. This is where the interval from A to B is partitioned. Partition just means that we've divided it up into smaller subintervals. Partitioned into n subintervals of equal length and I'm going to underline those words equal length because it's important that not always will you have subintervals of equal length, so we'll need to talk about what to do when you don't have that. But in this instance, in the definition, we're saying they are equal length. And that equal length is h, which is equal to the quantity b minus a divided by n. Basically, you're taking your interval and you're dividing it up into n subintervals. So from A to B, I'm dividing that up. So I find the difference. How long is that interval? And I divide it by how many intervals I want, subintervals I want, n subintervals. So divided by the number of subintervals I get, I can get what the length of each subinterval is. That's the height of your trapezoids. Okay, because if you have a curve, let's say like this, and we're wanting to fit trapezoids underneath here, okay, here's my x-axis. We're going to put a trapezoid underneath here. You can already see how that when I put a trapezoid, it's going to follow that curve a whole lot better. It's going to be a better estimate of the area under that curve. Trapezoids do give us better estimates than rectangles. If we were in class when we had done the rectangular approximation method, I would have asked, one question I would have asked you all, and I wished I'd asked it the other day in the video, could you think of a different shape that we could put under that curve to perhaps better estimate the area? And a lot of times students do say trapezoids. Trapezoids actually would be a whole lot better shape to estimate with. But you're basically fitting trapezoids of the same width underneath this curve. That one starts to look more rectangular there. Okay, and you're putting all of these trapezoids in here. And to find the area of each one of these trapezoids, we have to take the bases. We have to use the sum of the bases. We take half the height times the sum of the bases. This is like my y sub 0. Because this first one will be like my x sub 0. Here's x sub 1. I'll get those from how many subintervals do I want? What are those x values there? Okay? So I'm going to have, and again, the width of each one of these is h. All of these are h width. So that's h, that distance there is h. All of those are h wide. Okay? So, I take that and I look at my y sub 1, y sub 2. Those will be the y values at each one of these. Okay? When I find the area of this first trapezoid, the area of a trapezoid is 1/2 the height times the sum of the bases, b1 plus b2. Well, the thing is, y1 is a base for this first trapezoid, but it's also a base for the second trapezoid. That's why I'm going to have to add 2 of them together here. I can only use this formula, though, if they're all of the same width, which is h. They all have the same height. So that's why I'm using 2 times y sub 1 there, because all of the ones in between, all the way down to the very last one, the very last one will be y sub n, and the one right before that will be y sub n minus 1, whatever n minus 1 is, the one right before n. And when I fit that trapezoid in there, underneath there, I'm going to use this very last base only once, just like I only use y sub 0 once. That's why I'm not multiplying those by 2. But everything in between, all of those other bases in between, I'm having to multiply by 2 in my area formula. And I'm adding up the areas of all these trapezoids. So the first trapezoid is going to be half the height times y sub 1 plus y sub 0. The second one's going to be half the height times y sub 1 plus y sub 2. So all those ones in between are getting used twice. That's why the formula looks like this. I hope that makes sense. In the context here. That's only if they're the same width, if the h is uniform, okay, equal length. If it's not, most likely you're dealing with a smaller set of data, and you will have to just do each trapezoid one by one. Instead of using this equation or this formula, you'll have to do each trapezoid one by one. I almost think it's best to just do that anyways, but when you're dealing with a larger set of data with many subintervals, this is a lot better if your height, your width of your trapezoids, the width of your trapezoids, if that's uniform, it's a whole lot easier to do it quicker using this formula. Okay? But if it's not, if you're given a set of data and you're asked to do a trapezoid rule approximation for the area under that curve for the integral, and now I'm not going to necessarily say the area under the curve. I may just say approximate this integral. Well, to approximate that integral, that definite integral, that means to find the area under the curve. That's just another way to say that. So from now on, I can just say, hey, approximate this integral. Do it with a LRAM. Do it with an RRAM.
Time,
do it with a trapezoidal rule.
We apologize for the delay, but the buses are parked, and we appreciate you coming in today and look forward to seeing you in the morning. Thank you.
Pardon the interruption there. So that's how you'll go through and actually find the area underneath the curve. To approximate that integral, you can use the trapezoidal rule if they are of equal length. If not, do each trapezoid one at a time. Do the first trapezoid, get that area. Your height will change then, and you'll have to do the area formula. You'll have to do this area formula for each trapezoid in that case, if that's the case. Okay? All right, let's look at an example. Also, one other thing. Alternatively, before we go to the next thing here, before we go to an example. Alternatively, if I can spell correctly today, T is also equal to the LRAM plus the RRAM divided by 2. So alternatively, the trapezoidal approximation is also equal to the average, in other words, of the LRAM and the RRAM. You add them together and divide by 2. Okay? That's important to note because that means that approximation, the trapezoidal approximation, will always be in between the LRAM and the RRAM. We already know that with LRAM and RRAM that one of them usually is a little bit more of an overestimate and one of them is a little bit more of an underestimate. So getting in between obviously would make us a little bit closer to the actual amount, the actual area under that curve. Okay? So let's look at an example. Not rule. Let's use a trapezoidal approximation to estimate the integral from 1 to 2 of x squared dx with n equals 4 subintervals compare your answer with the numerical integral. Which the numerical integral, I'm talking about doing the integral on the calculator like we did yesterday. Okay, that's what I'm talking about when I say the numerical integral. So we'll actually type this integral in the calculator and get that numerical integral. So to do a trapezoidal estimate with n equals 4 subintervals, we need some data points here. Okay, we need some points here, some x and f of x points. So we're starting at 1 and we're going to 2. We need 4 subintervals. So we're going to need values in between 1 and 2. We're going to have to divide that up into 4 subintervals. So we'll need 1.25, we'll need 1.5, we'll need 1.75. From 1 to 1.25 is one subinterval. From 1.25 to 1.5 is another subinterval. From 1.5 to 1.75 is another subinterval. And from 1.75 to 2 is another subinterval. If you have to figure out to do this another way, you could do your b minus a divided by your n. That would be 2 minus 1, and you're dividing that by 4. So the height of each one of your little subintervals is 0.25. So you can add 0.25, 0.25, add 0.25, add 0.25, make sure that that works out. Okay, we need the function values at these points. We already know that 1, I plug 1 into x squared, I get 1. If I plug 2 into x squared, I get 4. So we need the values in between. So you can go to your table, type this in the calculator, your x squared function and y equals. Go to your table. Go to your table, input those values. 1, 1.25, 1.5, 1.75, and 2. Make sure I have those correct. And I get some answers here. Okay. So I get 1.5625, 2.25, 3.0625, and 4. Obviously, 4, well, we already have 1 and 4 on there. So I'll get my answers there. I'm going to go ahead and use every decimal point they give me on the calculator. I want to be as exact as possible here. These are all of equal width because we made them that way. If you're given a function and just asked to approximate, if you're just given an integral and approximate this with so many subintervals, you on purpose want to make it of equal length because it will make your life easier because you can use the shortcut with the formula. Now, if you're given a table of data, you're already given just a table of data and said to estimate this integral from whatever the starting x value is to the ending x value, then you're kind of bound to have to use that data then because you don't know anything else about the function. You hope that all the subintervals are equal width. You hope they're of equal length of each other, width or length. I keep using the word there. Switching words there that I'm using, guys. I'm sorry. You hope that your subintervals are of equal length, is what I mean to say. But they may not be, and if they're not, then you're going to have to treat each one as a separate trapezoid. You cannot use the formula I did. You'll have to do the trapezoid area formula for each subinterval. Here they are though, so we're good. So you'll take your height of your h value, which we found to be, we did 2 minus 1 divided by 4, was 0.25. That's what I have to add to get to each one of my x values there. Okay, so then I'm going to take 0.25 divided by 2 times the first y value, which is 1, plus 2 times 1.5625 plus 2 times 2.25 plus 2 times 3.0625 plus 4. And I'm going to type that in the calculator. So you do this with me if you're not already doing it. Pause the video if you need to. And I get an estimate. This is my trapezoidal estimate. I get an estimate of 2.34375. I'm just going to give every digit the calculator gives me. Of course, for the estimate there at the end, you could round that to 4 decimal places if you want to. Be 3437 or 2.3438 then in that case. All right, if we do a numerical derivative on the calculator, so if we actually do alpha window number 4, this is what we did at the very end of the day yesterday. You do 1 to 2 of x squared dx. So you type all that in. Alpha window number 4, you type all of that in right there just like it looks. And you hit enter. You get 2.3 repeating, with the 3 repeating there. So, the numerical derivative, the numerical answer, I get that, 2.3 repeating. So 2.34375, that's not a whole lot off. That's our estimate. It's a little bit more than the actual, but it's not much. It's pretty good. That's a pretty good estimate for the integral value. Okay? Again, I'm going to give you some problems today on a worksheet that I'm going to attach on Google Classroom for you to look at. I'm going to give you some problems today. I'm going to probably give you time today and maybe even a little bit of time tomorrow also to kind of work on those a little bit. So that way you've got some time, because it's also going to have you do some left and right rectangular approximations to compare them with the trapezoidal approximation. I think that's really good practice to do that. So I'm going to give you time to do to work on those. Some of these are AP test questions, so they're really good questions to actually look at to see how the AP test is going to look in regards to this. Okay, so I'm going to give you some time today and tomorrow to kind of wrap up all that stuff with approximations. So next week we can start in with some properties of integrals, definite integrals, and we're building up to 6.4 with the fundamental theorem of calculus, which is the biggest theorem probably in all of calculus. And that's where we're really going to get into this. Get into the relationship and how to find the exact area under the curve, how to do it analytically. Because everything we've done so far is estimating it numerically, geometrically, but we're going to do it analytically. All right. Hopefully this has been pretty clear. Again, remember, if your subintervals are of not equal length, if they're not of a uniform length like I made them be here, and like they are most of the time, but not always, if you're given a table of data, that's always where you got to be suspicious of this. Check to see that your subintervals are the same width. See if the difference between your x values, your consecutive x values, whether that's the same or whether it's different. If they're different, then you're going to have to treat each subinterval as its own trapezoid. You can't use this formula. You'll have to just do the area formula for the trapezoid so many times. I will say this, most of the time when that's the case, you're dealing with a smaller number of subintervals. I know there's going to be one on your worksheet or one on the practice somewhere that's going to have like 3 subintervals. Okay, so you're going to have to do that with 3 subintervals, but it's a smaller number of subintervals. So that would be 3 trapezoid area formulas to find the area of each one of those trapezoids and then add those up together. Okay? All right, let me know if you have any questions.